When 3I Atlas disappeared behind the Sun for 35 days, astronomers expected it to return on the same predictable path. It didn't. Instead, it re-emerged with a tiny but impossibly precise adjustment, one that redirects it straight toward a narrow gravitational keyhole near Jupiter. A course correction that shouldn't happen naturally, not from outgassing, not from thermal stress. Something altered its trajectory, and it did so with purpose. Now the destination is no longer uncertain, and the implications aren't terrifying because of speculation. They're terrifying because the numbers leave almost no other explanation. If you want science that cuts through assumptions and looks directly at the data, make sure to like and subscribe. Let's get into it. You do not usually expect the universe to surprise you, not after years of images, charts, and sky stories that make space feel familiar. But on a quiet night, when 3I Atlas finally emerged from behind the Sun after 35 days of total blackout, something showed up in the telescope data that did not fit. Atlas was off. Not by much, and not in a way most people would notice on a screen, but enough to stop trained observers mid-sentence. The change sat inside a thin line of numbers that should have followed the same pattern as before. Instead, the line refused to behave. The difference was a fraction of a degree, so small it could slip past the eye if you were not looking for it. In deep space, though, small angles add up. A tiny shift in direction, applied far from the Sun, can move an object millions of miles away from where it was expected to be weeks or months later. That is normal math. What was not normal was what the shift meant this time. The new track did not send Atlas away from anything in particular. It aimed Atlas towards something very specific. The first person who saw the mismatch did what scientists always do when a result feels wrong. The orbit fit was run again, then again, checking for simple mistakes. The timestamps were checked. The reference stars used to measure the position were checked. The software settings were checked. Another person repeated the work independently. The result stayed the same. That is when a room gets quiet, not because of fear, but because everyone is listening for the one explanation that will make the numbers ordinary again. It did not arrive. Atlas had not drifted off the predicted path in a random way. It had moved onto a new one, a cleaner line that extended forward into a narrow thread of space more than 500 million miles away. That thread had a name that sounds almost casual until you understand what it means: Jupiter's keyhole. Most people picture the solar system like a flat map, with neat oval orbits around the Sunday. That picture is useful, but it leaves out the parts that matter most in problems like this. The keyhole is not a physical object, and it is not a place you can point to on a regular chart. It is an invisible boundary tied to Jupiter's gravity, a tiny slice of space where a passing body can be redirected in a big way. Think of it as a narrow gate in the larger flow of motion around Jupiter, where the timing and the approach line up so precisely that the planet's pull reshapes the path that follows. The region is narrow compared with the emptiness around it. Hitting it by accident is hard. When researchers talk about odds around 1 in 26,000, they are describing how rarely a random approach would land on the same kind of corridor. Space is huge, and Jupiter's influence is strong, but the exact corridor that leads to a very specific outcome is thin. This is where normal comet behavior matters. Many comets do not fly like smooth, silent stones. They spin. Their surfaces heat unevenly. When sunlight warms ice, gas can leak out, and that jet of gas acts like a weak thruster. Scientists call these non-gravitational forces. They are real, measured, and often small, but they can nudge a comet sideways over time, because jets can turn on and off. and because the surface is rough, those pushes can be hard to predict in detail. That is why comets often wobble in their long-term forecasts. A tiny burst today can become a large miss months from now. Atlas did not look like that kind of case. In the data, the motion did not wander. It tightened. It slid onto a line that looked unusually clean, as if the object had been placed onto a track that already knew where Jupiter's unseen border would be. It is important to say what this does and does not mean. A clean line does not prove purpose. Scientists do not assign intent to a rock or an icy body just because its path is neat. They treat the neatness as a clue that the forces were simple, steady, or well-timed. Still, it is fair to notice how unusual it feels. Most natural objects in space show some messiness when you look close enough. When an object from outside the solar system comes in and threads a narrow gravitational doorway with high accuracy, it draws attention for a basic reason. The solar system is not a quiet lab. It is full of pushes and pulls, and precision is rare. That is why the 35 days behind the Sun become part of the question. When Atlas passed into solar conjunction, Earth could not track it well. The glare of the Sun overwhelms sensitive detectors, and the geometry puts the object in a blind spot. Solar radiation and interference also make measurements harder. For a while, there is simply no clean line of sight. That blackout does not create mystery by itself. It is a normal observing gap that happens with many objects, but it does create a window where small changes could occur without being seen in real time. A tiny push from outgassing, a subtle change in spin, even a brief release of material could alter the future path by a small amount. Nobody on Earth would catch that moment directly. The first clear sign would come only when the object reappeared and the new measurements were compared to the old prediction. When Atlas came back into view, the response was not panic. There was no sign of immediate danger. The new path did not point toward Earth, and nothing in the early numbers suggested an impact risk. There was no reason to call it a threat. The unsettling part was not the destination itself. It was the way the object seemed to reach for that destination with so little scatter. Researchers do not need drama to feel a strong pull of curiosity. The pull comes from a simple question that is easy to state and hard to answer. How does an object arriving from another star system glide so smoothly into a corridor that is wide on a human scale, yet mathematically tiny in the scale of the solar system? To understand why that tiny mismatch matters, it helps to follow where the new path leads, not just toward Jupiter, but toward a structure around Jupiter that no camera can see. Jupiter is famous for its colored bands, its storms, and its bright moons. But the feature that controls trajectories is not visual, it is gravitational. If you could turn off the planet's visible surface and look only at how it shapes motion, you would not see clouds. You would see a deep dent in the space around it, a region where paths bend toward the planet more than they would otherwise. The Sun makes the deepest dent, of course, because it holds the whole system together. But Jupiter makes its own. And for nearby objects that dent can dominate, Jupiter does not merely orbit the Sun like a simple point. Its mass changes the motion of anything that passes close enough, pulling and redirecting it in ways that can be measured. That reach is often described with the idea of the Hill sphere. This is not a hard shell you can bump into. It is a way to mark a zone where Jupiter's gravity begins to compete with the Sun's gravity for control over a smaller object. Inside that zone, Jupiter can hold moons and capture passing debris more easily. Outside it, the Sun's pull dominates more strongly. On paper, Jupiter's Hill sphere is roughly 52 million kilometers from side to side. The number is large, and that can make it sound like a simple, giant bubble. A useful mental picture is an enormous transparent region around Jupiter where the balance of forces shifts. It is not a wall, but it is a change in who has the stronger vote over the path. Now, imagine approaching that region from far away. At first, you feel almost nothing from Jupiter. The sun still sets the main direction of motion, and Jupiter is just another bright point. But as the distance closes, Jupiter's tug grows. The increase is not sudden. It builds. The way gravity works, it gets stronger fast as you get closer. That is why a small change in approach can make a large difference later. A path that passes slightly above or below a certain line can end up on very different tracks after the encounter. This is the heart of a gravity assist. When a spacecraft uses a planet for a slingshot, it is not stealing energy in a simple cartoon way. It is exchanging momentum with a moving planet through gravity, changing its direction and speed relative to the Sunday natural objects can do the same thing. If the approach geometry is right, Jupiter can bend the path sharply or gently, and that bend can send the object inward or outward in the solar system. The key detail is that the Hill sphere is not an on and off switch. Near its edge, there are narrow regions where the pull from Jupiter and the pull from the Sun nearly balance in a fragile way. In that thin zone, very small differences matter. Trajectory analysts often talk about this using the idea of a keyhole because it captures the shape of the problem. There is an opening that leads to a specific outcome, and the opening is narrow. In more technical terms, this comes down to how closely the object passes Jupiter and how precisely its approach aligns with a very narrow plane of motion. But the basic idea is simple. Approach slightly too high or slightly too low, and the corridor is missed entirely. The object remains bound to the Sun on a path that is altered only marginally. Approach within just the right band, however, and Jupiter's gravity redirects the trajectory onto a fundamentally different track. The margin for error is extremely small. And that is the framework astronomers had in mind when they examined where Atlas was headed. When they extended the revised trajectory forward in time, the abstract idea turned into a concrete result. Atlas was not merely passing through Jupiter's general neighborhood. The calculations showed it skimming the edge of Jupiter's Hill sphere at a distance of roughly 60,000 kilometers from the mathematical boundary. 60,000 kilometers may sound substantial on its own, but against the full scale of the Hill sphere, which spans approximately 52 million kilometers from side to side, it represents an exceptionally tight alignment. On that scale, the margin is vanishingly small. It is the difference between passing near something and passing through a very specific layer of space. When teams at the Jet Propulsion Laboratory and the European Space Agency ran independent analyses, the result converged on the same conclusion. The odds for a random, unsteered interstellar object to graze that particular shell at that distance and at that angle came out to roughly 1 chance in 26,000. That number matters not because it is dramatic, but because it describes how rarely this kind of alignment should appear by accident. A single coincidence can always be waved away. Patterns that require multiple conditions to line up at once are harder to ignore. Here, the distance, the timing, and the approach geometry all had to fall within narrow limits. Random paths through the solar system usually miss such regions entirely. They pass too far out, or dive too deep, or arrive at the wrong angle. This is why researchers say objects do not simply stumble into Jupiter's keyhole. They reach it only under very particular circumstances. That realization sits quietly in the background as you think about what Atlas is supposed to be. Icy bodies and comets are not known for clean behavior. Their surfaces are uneven. Sunlight heats them from one side, then another. Ice turns directly into gas, a process called sublimation, and that gas escapes through cracks and weak spots. Each release acts like a tiny push. Over time, those pushes add up, but they do so unevenly. The result is usually a slow smearing of the trajectory. The path becomes fuzzy at the edges. Predictions spread out instead of tightening. Nature, at this scale, is noisy. It does not usually draw straight, narrow lines through space. In theory, outgassing could nudge a body closer to a sensitive region, like the edge of a hill sphere. A jet of vapor on the right side, at the right moment, could make a difference. But there is an important detail here. Those jets are not aimed. They are not coordinated. They tend to push objects away from delicate balances rather than into them. Most of the time, non-gravitational forces increase uncertainty instead of reducing it. They turn clean curves into wandering paths. Atlas did the opposite. The best-fit solution after it emerged from behind the sun showed a trajectory that threaded this thin gravitational boundary with unusual accuracy. This is why the probability estimate lingers. One chance in 26,000 is not a magic threshold, and scientists do not treat it as proof of anything by itself. What it does is describe how rarely a configuration like this should arise without some specific influence shaping it. Random motion does not usually place objects on such narrow corridors. Precision, especially quiet precision, stands out in orbital mechanics. It does not trigger fear. It triggers closer inspection. At the same time, there is no practical reason for alarm. Jupiter remains more than 600 million kilometers away. The keyhole is not a gateway to disaster. Atlas is not headed toward Earth, and nothing about its path threatens daily life in any direct way. What is happening is remote, detectable only through careful measurement and long-term tracking. For most people, it exists only as a faint dot in archived images and a curve on a graph. The unease that follows this story is not about danger. It comes from the question of how such order appeared where disorder is expected. That question naturally leads back to the period when Atlas was hidden from view. For 35 days, it passed through solar conjunction, moving behind the sun from Earth's perspective. During that time, observation is effectively impossible. The sun's glare overwhelms optical systems. Detectors saturate. Signals are drowned in noise. This is a routine problem in astronomy, not a failure. Objects disappear into that bright zone and reappear weeks later, and most of the time they come back exactly where the equations say they should. Before Atlas entered that blind spot, its motion was well constrained. Gravity is predictable when you know the masses and positions involved. If nothing unexpected happens, an object returns on schedule, right on its forecast track. That was the expectation here. There was no reason to anticipate a surprise. But when Atlas emerged on the far side of the sun, the position was just slightly off. Not enough for a casual glance to catch, but enough for the software to flag it immediately. The difference was tiny, like a millimeter error on a ruler or a compass needle, hesitating for a brief moment before settling. Small, but real. The natural response was to assume a mistake. The orbit was recalculated. Different reference data were used. The process was repeated. The offset remained. The only way to reconcile the observations with the equations was to add a new term to the model. That term represented a very small acceleration acting on Atlas during the blackout period. Not a dramatic force, not a sudden shove, just a gentle, sustained push spread over many days, too subtle to notice in a single image, but strong enough, over time, to alter the future path. This kind of effect is known as non-gravitational acceleration. In most cases, it comes from outgassing, as ice on a comet's surface turns into vapor under solar heating. These forces are common in the outer solar system. Icy bodies constantly release tiny amounts of gas. The surprise with Atlas was not the existence of such an acceleration, but its character. The inferred value was on the order of 5 × 10⁻⁷ astronomical units per day squared. That number is extremely small. It describes a force that is almost negligible moment to moment, yet when applied steadily across roughly 30 days, it produces a shift just large enough to matter. More important than the size was the direction. Instead of adding randomness, the acceleration aligned Atlas more closely with Jupiter's keyhole. It reduced uncertainty rather than increasing it. It nudged the object toward a very specific gravitational edge. In simple terms, it acted less like a series of random hisses and more like a single, well-placed breath. Here is where the usual explanations begin to strain. Natural outgassing does not behave this cleanly. Comets tumble. Their jets turn on and off as surfaces rotate in and out of sunlight. Gas sprays in multiple directions. The resulting motion looks jittery when analyzed carefully. It does not produce smooth, efficient corrections aimed at rare orbital corridors. It certainly does not tend to place objects onto paths that statistical models say should appear only once in tens of thousands of tries. This does not mean that Atlas is being controlled or guided in any intentional sense. Scientists are careful about that line. No one is claiming a steering system or an artificial hand. What the data suggest is something more subtle and more challenging. A force acted at just the right time, in just the right way, to shape the trajectory with surprising efficiency. It is the kind of result that does not fit neatly into the patterns researchers are used to seeing. That is why the response has been one of pause rather than panic. When natural objects experience non-gravitational forces, they usually behave like pebbles kicked across uneven ground. The motion becomes rough, predictions spread out. Atlas behaved as though it had been nudged with care. Not hard, not often, just enough. Natural processes do not usually optimize outcomes. They do not aim, they do not guide, and they do not, as a rule, deliver objects onto 1 in 26,000 trajectories that skim the edge of a planetary gravity boundary with near surgical accuracy. None of this implies danger. Whatever occurred while Atlas was hidden behind the sun did not threaten Earth or alter the overall safety of the solar system. It simply reshaped the object's path, directing it toward one of the most delicate gravitational thresholds Jupiter offers. Somewhere during that 35-day blackout, when Atlas was lost in solar glare, its trajectory shifted. The change was minimal. A faint, non-gravitational push, an acceleration too small to observe directly at the time, but one that becomes clear when the motion is reconstructed afterward. Understanding why that small change matters requires looking at how orbital motion behaves over long distances. Space does not soften small errors. It amplifies them. A difference that appears insignificant in a single night of tracking can translate into a radically different position weeks or months later. This is why the situation does not call for drama, but for careful attention. Orbital paths are highly sensitive, especially for small bodies far from Earth and subject to multiple subtle forces acting over time. When researchers talk about an orbit, they are not thinking in a simple, "where is it?" way. They describe motion with a full 6-dimensional state. That just means 6 values that define the object at a given moment. 3 values describe position in space, where it sits relative to a reference frame. 3 more values describe velocity, how fast it is moving, and in what direction at that same moment. If any one of those 6 values drifts even slightly, the future path changes. A tiny change in speed today can become a large shift in distance later. A small offset in position, if carried forward through time, can turn into a miss, measured in millions of kilometers. This is normal. It is why orbit predictions always come with uncertainty bands. Astronomers do not get one perfect line and call it done. They get a best fit line plus a cloud of possible lines around it, based on measurement limits. Telescopes have small errors. The object's image can be faint. The exact center of the point of light can be hard to measure. Even the background star catalog has tiny uncertainties. Then there is the physics. Gravity is the main driver, but it is not the only driver for icy bodies. All of those small uncertainties become part of the orbit solution. In most real cases, that uncertainty cloud grows with time. The farther you project into the future, the wider the possible path becomes. That widening is the noise you expect to see. With many comets, the widening happens faster because the object is changing as it warms. Gas release can start and stop. Dust can lift off the surface. The object can spin in a way that changes which areas get heated. Those effects do not usually line up neatly. They push in different directions at different times, so the predicted path becomes less tidy, not more. That is why Atlas is unsettling in a very quiet way. When astronomers look at the updated fit, they do not see random scatter that washes out over time. They see a consistent, lean, every small deviation that has been measured, every minor adjustment needed to match the observations, seems to point the same way. The corrections do not fight each other. They do not cancel out. They do not spread out like a messy spray. Instead, they tighten the story toward one outcome, a closer, cleaner approach to Jupiter's Hill sphere, and toward that razor-thin region near the edge that people call the keyhole. It helps to be clear about what keyhole means in simple terms. It is not a door you can see. It is a narrow region of approach conditions. If the object passes through that region, Jupiter's gravity bends the path in a very particular way afterward. If it misses that region by a small amount, the bending happens differently, and the later path is not the same. The keyhole is thin because the allowed range of distance and angle is narrow compared with the vast empty space around Jupiter. So when a body appears to be lining up for that kind of pass, scientists pay attention, because lining up is the hard part. Now think about the body itself. Most comets do not behave like stable machines. Their surfaces are uneven mixtures of ice, rock, and dust. When sunlight reaches them, the heating is not uniform. One patch might be darker and warm more. Another patch might be covered in dust and stay cooler. Cracks open as material expands and contracts. When gas escapes, it does not always escape in the same direction, and the force it creates is usually small but unpredictable. Over time, this produces a kind of natural jitter in the motion. It is not chaos in a dramatic sense. It is just the normal result of an active, rotating, uneven body responding to sunlight. So if Atlas is an icy body, you would expect signs of that jitter, especially after the long period when it was unobservable behind the Sunday. During solar conjunction, you cannot watch the day-to-day changes. You lose the ability to see small accelerations as they happen. If outgassing occurs in that time, you do not record the exact timing. You only see the final result when the object reappears. In most cases, that creates more uncertainty. You would expect the orbit fit to get less clean, not more. But the new fit for Atlas behaves as if the unobserved forces did not add randomness. Instead, they added direction. That is the heart of the puzzle. The non-gravitational acceleration inferred during the blackout period was extremely small, on the order of 5 times 10 to the -7 astronomical units per day squared. But over many days, a force that's small matters. In everyday terms, it is like a long, gentle push rather than a sharp shove. The surprising detail is not the size. It is the way the push lines up with the rare corridor that leads toward Jupiter's keyhole region. There are natural ways to get a directional push, at least in principle. If gas escapes mostly from one persistent vent, and if the spin of the object keeps that vent facing in a similar way over time, the net force can be steadier than random bursts. If the object's rotation is slow, or if its spin axis is oriented in a stable direction, a single active area could push more consistently. Dust can also play a role. Dust particles leaving the surface can carry momentum away, which can act like thrust. Sunlight itself can push on dust and gas in subtle ways, and that pressure can shape a coma and tail, which affects how material escapes. None of these ideas require anything exotic. The problem is that even these natural explanations usually leave fingerprints of messiness. A vent can weaken, shift, or clog. Rotation can change due to torques from gas escape. Activity can move as new cracks open. If you track enough comets closely, you usually see that their non-gravitational forces vary with time. The best fit acceleration changes sign or changes direction. The uncertainty grows. The orbit prediction becomes less narrow. That is the typical pattern. Atlas is showing something closer to the opposite pattern. The path looks smooth across distances measured in hundreds of millions of kilometers. It holds alignment across conditions that should introduce irregular behavior. If you imagine all the small influences that can act on a body like this: uneven heating, minor outbursts, surface cracking, dust release, gentle pressure from sunlight, each one should add a little bit of scatter, even if each effect is tiny. The combined result over weeks or months is usually not a clean line. Yet Atlas continues to look like it is following a narrow channel. This is why the focus returns again and again to precision. In orbital mechanics, precision is not a feeling. It is a measurable property of the fit. It shows up as small residuals, meaning the differences between what the model predicts and what the telescope actually sees. It shows up as a trajectory arc that does not need many messy corrections to match the data. It shows up as an uncertainty band that does not balloon as quickly as you would expect for an active icy body. When multiple teams run their own analyses and the results converge, that also matters, because it reduces the chance that the cleanliness is just a software artifact. It is also important to separate two ideas that can get mixed together. A tidy path does not prove control. It does not prove intention. It does not prove engineering. Science does not work that way. What a tidy path does is raise the value of the question. If an object behaves in a way that is rare for its category, you treat it as a special case, and you test explanations more carefully. You look for the simplest causes first. You check assumptions. You improve observations. You do not jump to a conclusion, but you also do not ignore the oddity. That is where Atlas sits right now, in the logic of the data. The object is far away. The keyhole is not aimed at Earth. There is no direct threat. What exists is an unusual form of order, a trajectory that stays steady when steadiness should be hard. A set of deviations that all lean the same way when you would expect them to scatter. A path that looks shaped rather than smeared. If you let that sink in, what you feel is not fear. It is a sharpening of attention. The more you look at the numbers, the more the motion resembles something gently guided by consistent physical effects, not steered like a craft, not controlled like a machine, just shaped as if the usual fingerprints of natural outgassing are quieter than they should be, or arranged in a way that produces an unusually clean result. And that quietness matters. In a system as large as the solar system, you can always find strange single events. But when the strangeness is not a burst, not a flare, not a sudden turn, and instead is a steady, orderly line, it becomes harder to dismiss as a one-time glitch. It becomes the kind of puzzle that asks you to keep watching, because the next measurements will either add noise and make the story ordinary again, or they will keep reinforcing the same narrow track. A tiny nudge should usually fade into the background. It should be swallowed by natural irregularities. In this case, it has not been swallowed. It has become a trajectory that stays too neat over too long a distance. A force too small to see has shaped a line too clean to ignore. There is no need for urgency here, no need for alarm. What remains is a calm, steady sense that the universe has posed a question in a very quiet way, and the only thing it asks from you is patience and careful attention. After all this attention to precision, one question follows naturally. If the trajectory is this clean, this carefully aligned, why does it lead toward Jupiter at all? Why not anywhere else? To answer that, it helps to stop thinking of the solar system as a collection of bright objects and start thinking of it as a landscape shaped entirely by gravity. Imagine removing every visible feature. No sunlight, no reflected glow from planets or moons, no colors, no clouds, no rings. What remains is a structure made only of force. In that stripped-down view, space is no longer flat or empty. It becomes a terrain of slopes and basins, shallow rises and deep wells, formed by mass. In that landscape, one feature dominates almost everything else. Jupiter would rise like an enormous mountain made of invisible weight. If gravity could glow, Jupiter would be the brightest structure in the solar system after the Sunday. Its mass is overwhelming. Jupiter contains more than 300 times the mass of Earth. In fact, it outweighs all the other planets combined. That single fact explains much of its influence. Mass bends space, and Jupiter bends it deeply. Because of that mass, Jupiter does not simply move along its orbit as a passive participant. It actively reshapes the motion of nearby objects. Asteroids collect around it. Comets have their paths redirected by it. Streams of debris are trapped, scattered, or stabilized by its pull. Like a massive boulder in a flowing river, Jupiter causes material to pile up, swirl, and reorganize around it. This is not a poetic image. It is exactly what orbital simulations show when Jupiter is included or removed from models of the early solar system. The region where Jupiter's influence becomes competitive with the Sun's is vast. Its hill sphere extends more than 50 million kilometers across. Within that region, Jupiter can hold moons, capture passing objects, and sculpt trajectories in ways no other planet can. This is not just a local effect. Over long timescales, Jupiter acts as a gatekeeper, shaping migration paths and stabilizing certain regions while destabilizing others. It is one of the main reasons the inner solar system looks the way it does today. And Jupiter does not exist alone. It brings with it an entire system. At least 79 known moons orbit the planet, each occupying its own niche within Jupiter's gravitational domain. Some of these moons are among the most scientifically important bodies we know. Europa, with its thick ice shell and a global ocean beneath, warmed by tidal forces. Ganymede, the largest moon in the solar system, massive enough to generate its own magnetic field, something no other moon does. Io, locked in an endless cycle of tidal stress, erupting with lava and feeding a vast plasma environment around Jupiter. Callisto, ancient and heavily cratered, preserving a record of early solar system history that has been erased elsewhere. Seen from a distance, Jupiter is less like a single planet and more like a miniature solar system of its own. Moons, rings, trapped particles, magnetic fields, and stable orbital regions all orbit the giant together. From a strategic point of view, this makes Jupiter unusually valuable. Not valuable in a human sense, but dynamically. It is a place where many processes converge, a place where matter, energy, and motion interact in complex but predictable ways. If you were studying the solar system with intent, Jupiter would be a natural focus. Its moons contain ice, rock, metals, and chemical environments, unlike those found elsewhere. Its magnetic field is immense, creating radiation belts that can be destructive, but also regions of relative stability where particles are trapped and guided. Its gravitational influence creates pockets where objects can remain for long periods without dramatic changes to their orbits. Then there are the Trojan asteroids, two vast swarms of objects that share Jupiter's orbit, one leading and one trailing the planet. These swarms sit in stable gravitational locations, balanced between Jupiter and the Sunday. Objects placed there can remain for millions, even billions of years. They are quiet regions, distant, cold, and rarely observed in detail. In terms of orbital mechanics, they are natural storage zones. This context matters when thinking about visibility. Earth is not a quiet place. It is one of the most closely monitored locations in the solar system. Radar systems scan nearby space. Optical surveys sweep the sky every night. Radio telescopes listen constantly. Satellites orbit the planet in dense shells. Earth is bright, noisy, and crowded with instruments. Anything passing near Earth is quickly noticed, catalogued, and tracked. Jupiter is different. It sits far from the Sun, in a region where sunlight is weaker and observation is more difficult. We do not monitor its surroundings continuously. Missions to Jupiter are rare and separated by many years. Telescopes look at it often, but not with the same constant attention given to near-Earth space. Large volumes around Jupiter remain comparatively quiet in terms of observation. It is not neglected, but it is not watched in real time, night after night, the way Earth's neighborhood is. From a purely scientific perspective, this makes Jupiter an interesting place. It is dynamically rich, but observationally sparse. It is massive enough to shape trajectories, but distant enough to remain partially hidden. If there were ever a region in the solar system where something could pass, linger, or be captured without drawing immediate attention, Jupiter's domain would be high on the list. None of this implies intention. There is no claim here of purpose or design, but it does explain why Jupiter matters when discussing a precise trajectory. Of all the possible destinations an interstellar object could approach, Jupiter is one of the most consequential in terms of dynamics and information. It is where long-term models of the solar system converge. Its position anchors migration patterns. Its mass dominates stability analyses. It is, in a very real sense, the anchor of the planetary system beyond the inner worlds. Some physicists have summarized this idea by saying that if you want to understand the solar system's structure, you start with Jupiter, not because it controls everything in a simple way, but because its influence appears in almost every serious dynamical calculation. Jupiter shapes what stays, what leaves, and what remains stable over time. So when Atlas's trajectory points toward Jupiter rather than toward Earth or Mars, it draws attention for a reason. It is not headed toward the loudest, brightest, most watched part of the system. It is headed toward the giant that creates deep gravitational wells and long-lived hiding places, a place built for permanence rather than immediacy. If Atlas does approach Jupiter closely, it approaches a region where objects can linger. They can be captured temporarily. They can be redirected into stable orbits. They can slip into Trojan swarms or skim magnetic environments that are poorly sampled. Jupiter's domain is not just a passageway. It is a reservoir. Let that idea settle without urgency. The mystery here does not need intensity to hold attention. It gains weight from scale. Jupiter provides scale in a way no other planet can. A gravitational fortress, not in a military sense, but in a physical one. A place where motion slows, bends, and reshapes itself. And near that fortress, there is already a witness. Far from Earth, orbiting Jupiter in a long, looping path, a small spacecraft has been moving quietly for years. It does not dominate the scene. It does not search the sky aggressively. It simply circles the planet, powered by sunlight that arrives thin and weak at that distance. One orbit takes about 53 days. The spacecraft is Juno. Juno was not sent to wait for interstellar visitors. It was designed to study Jupiter itself, its atmosphere, its magnetic field, its deep structure, its auroras. Yet by circumstance alone, it now occupies a unique position. It is the only human-made instrument operating in close proximity to Jupiter as Atlas approaches. Juno's orbit is highly elongated. It dives close to the cloud tops, then swings far out again, repeating this motion in a steady rhythm. With each pass, it collects data, not flashy images alone, but measurements, radio signals that probe the planet's interior, magnetic readings that map invisible fields, particle counts that reveal how charged matter moves around the giant. Among its instruments is JunoCam, a visible light camera best known for its images of swirling clouds and storms. Those images are visually striking, but the camera is also sensitive enough to record faint points of light under the right conditions. There is an infrared mapper, GIRAM, which reads heat patterns and can detect warm or reflective objects even in cold environments. There is an instrument called WAVES that listens to radio emissions and plasma interactions, capturing sounds of space that cannot be seen. Juno also carries particle detectors, known as JADE and JEDI, which measure high-energy ions and electrons. These instruments are designed to study Jupiter's radiation environment, but they are also sensitive to disturbances. An unusual spike, a strange flow, or an unexpected signal could stand out against the background. Taken together, Juno is not a lookout scanning the sky, but it is a quiet observatory embedded in Jupiter's domain. If something unusual were to pass nearby, reflect sunlight, emit heat, disturb plasma, or produce a radio signature that does not match known sources, Juno would be in a position to notice. It is equally possible that Juno will detect nothing at all. That outcome matters just as much. In science, silence is not failure. Silence is information. It constrains possibilities. It tells you what did not happen, which is often as valuable as knowing what did. So as Atlas continues along its precise path toward Jupiter's gravitational realm, the story does not hinge on spectacle. It hinges on geometry, mass, and quiet measurement, a carefully shaped trajectory leading toward the most influential planet in the solar system, a region rich in stability and complexity, and a single, patient spacecraft already there, listening. If Juno detects nothing at all, no unusual glint, no strange heat pattern, no radio burst that stands out from Jupiter's normal environment, then Atlas is behaving like a natural object. That outcome would support the simplest explanation for the tiny push during the solar blackout: ordinary non-gravitational effects, most likely outgassing from warmed ice, or a small change in how the surface vents gas as it rotates. It would also suggest that the clean alignment toward Jupiter's keyhole was coincidence layered on top of normal physics. Even a lack of signals can be useful. In space science, nothing unusual is still a result. It helps narrow what is possible, and it reduces the need for exotic explanations. At the same time, there is a realistic middle ground between nothing and something dramatic. Juno could notice something subtle, a small moving point against background stars that is steadier than expected, a faint change in infrared brightness that does not match common dust or ice behavior, a brief radio feature that does not fit the usual patterns Juno records around Jupiter. Jupiter's space environment is busy in its own way. Its magnetic field drives strong auroras. Charged particles move along field lines. Radio emissions can rise and fall like a complex shifting chorus. Because that environment already produces many natural signals, the main challenge is not detection. The challenge is interpretation. A single odd feature might be noise. A repeatable feature that appears at the right time and in the right direction becomes more interesting. Most likely, Juno will not see anything outside the normal range. That is the most common outcome in careful observation. But if Juno does register something that does not fit, the meaning would be large for a simple reason. It would be the first time a human-made spacecraft had a chance to watch a visitor from another star system near a major planet up close, not just from Earth-based telescopes. Nearly all of our instruments are built to watch the inner solar system. Earth watches Earth. Mars is observed constantly. Mercury and Venus are seen often because they are close and bright. Jupiter is different. It is far away, harder to monitor continuously, and usually studied in brief bursts when a mission arrives. Juno, with its long looping orbit, is the closest thing we have to an active observer already in place. It was not sent to act as a lookout for interstellar objects, but it has instruments that can catch clues without needing to hunt in the way a dedicated survey telescope does. It measures infrared light, visible light, radio and plasma signals, energetic particles, and the shape of Jupiter's magnetic field. Those tools were designed to study Jupiter, yet they can also serve as a sensitive background monitor. If something passes through Jupiter's region and disturbs the local environment even slightly, Juno is one of the few devices close enough to record it. The timing is part of what makes this worth following carefully. By March 2026, Juno is expected to swing through a part of its orbit that lines up unusually well with the region where Atlas is projected to pass. Not at the same point, and not close enough to create a risk to the spacecraft, but close enough that watching could happen almost automatically if the geometry is favorable. In other words, Juno does not need to chase Atlas. It just needs to be in the right place at the right time with the right instruments active. That kind of alignment can happen by chance, and it often does in orbital mechanics. Still, when you place it next to the earlier alignment of Atlas toward Jupiter's keyhole, it creates a sense of anticipation that is calm rather than urgent. Something might be recorded, or nothing might be recorded. Either way, the record will matter. If Juno sees nothing unusual, the story becomes more grounded. The clean path becomes an example of how rare coincidences can still occur in a system this large, especially when you are filtering millions of possible trajectories down to a few that pass near sensitive gravitational regions. If Juno sees something, even something small, then the story changes in a different way. It becomes a new kind of dataset, one that links an interstellar visitor to close-range measurements near a giant planet. The goal is not to confirm a thrilling idea, The goal is to sort possibilities from impossibilities with evidence. That brings us to the next question that people naturally ask when they see too clean motion. What if Atlas is not just drifting, but doing something deliberate? This is where careful language matters. Science does not treat that idea as the default, and it should not be treated as the first explanation, but it is fair to describe why the idea exists, what it would require, and what evidence would be needed to take it seriously. One reason this topic comes up at all is that an icy body can hide a lot. Comets are, by nature, good at looking ordinary from far away. A dark, carbon-rich surface absorbs light. A dusty outer layer can mask sharp edges. If the object releases gas and dust as it warms, it creates a coma and a tail, which are familiar features that astronomers see all the time. That familiar behavior can make it harder to notice something unusual inside, if anything unusual exists. This does not mean there is something hidden. It only means the outer appearance is not always a clear guide to the internal structure. This kind of discussion became more public after the interstellar object named Oumuamua passed through the solar system in 2017. Oumuamua was detected late, already leaving. It had unusual properties in the light it reflected, and it showed a non-gravitational acceleration that some researchers debated. One scientist, Avi Loeb, argued publicly that it could be consistent with an artificial light sail, meaning a thin structure pushed by sunlight. Many other scientists disagreed and argued for natural explanations, including outgassing that was difficult to detect, or an unusual shape and composition. The debate was not settled by opinion. It remained limited by data quality. Oumuamua was faint, distant, and observed for a short time. There was simply not enough information to close every possibility. Atlas is different from Oumuamua in several ways. Oumuamua appeared dry, with no clear coma or tail. Atlas, in the scenario you are tracking, behaves more like a comet. It shows activity, consistent with gas and dust release. That makes ordinary outgassing more plausible. At the same time, Atlas also shows a kind of trajectory cleanliness that feels unusual for an active icy body, especially when the inferred push during solar conjunction appears to align toward a rare gravitational corridor near Jupiter. That combination is what keeps the question alive, even if the safest conclusion remains natural until proven otherwise. If someone wanted to argue for an artificial component, they would need to answer a simple practical question. How could an object cross interstellar space without obvious engine exhaust, without a bright plume, and without constant thrust? The key is that interstellar travel does not require loud thrust if you are willing to take time. There are propulsion ideas that rely on very weak forces applied for very long periods, or strong forces applied only at the beginning, with long coasting afterward. None of these require breaking physics. They are difficult for humans to build today at scale, but the principles are understood. One option is a solar sail. This is a large, thin surface that uses pressure from sunlight. Sunlight carries momentum. When photons reflect or are absorbed, they transfer a tiny push near a star. That push can be small but steady. Over weeks, months, and years, steady small pushes can add up. A solar sail does not need fuel. It needs area, low mass, and time. If such a sail were used early in a journey, it could help shape a trajectory without the heat signature of rocket exhaust. It would also produce non-gravitational acceleration that could look smooth rather than bursty, depending on the sail's orientation. Another option is a magnetic sail. Instead of using light, It uses charged particles. Stars emit streams of plasma, and interstellar space contains charged particles as well. A large magnetic field could interact with that flow, creating a drag or a steering force. This would be subtle and would not necessarily create a bright, visible signature. It could help slow an object when entering a new star system, or adjust its approach angle without venting gas. The challenge is that generating and maintaining a large magnetic field requires energy and hardware, and the details depend strongly on design. Still, the physics of magnetic interaction with plasma is real and already used in many space science models. A third idea is beamed propulsion. In this concept, a powerful laser or microwave array pushes a sail or a light structure early in its journey. The pushing device stays behind, and the craft coasts for a long time. By the time it reaches another star system, it may be mostly silent, with no active engine. If it needs course correction, it might rely on tiny maneuvers, small enough to hide within normal measurement noise unless tracked very carefully. Again, this does not require fantasy. It requires enormous engineering, but the basic physical idea is straightforward. If a craft were built to move quietly, it would not need to make big maneuvers near a target system. It would only need small corrections at key times. That is the important point. In orbital mechanics, a small push applied at the right time can produce a large change later. This is exactly why gravity assists work, and why keyholes matter. If you can place an object on the correct approach corridor, a planet's gravity does much of the work for you. The object does not need to burn fuel the whole way. It only needs to arrive with the right geometry. This is also why some people focus on the timing of Atlas's inferred push during solar conjunction. That 35-day blackout is a period when we cannot monitor the object's behavior in detail. A small course correction during that window would be hard to see directly. We would only infer it afterward from the changed trajectory. If you are trying to hide a minor adjustment from distant observers, acting during solar conjunction would be an effective way to do it. This reasoning is logical. The missing step is evidence that such a hidden adjustment actually happened in a deliberate way, rather than through ordinary outgassing that we simply did not observe in real time. There is also a basic engineering argument people bring up: durability. A system traveling between stars would not need to stay active the whole time. It could shut down most functions and wait. It would not need a crew. It would need endurance. It would need shielding from radiation and micrometeoroids. It would need thermal stability. A thick, icy body provides natural shielding. Ice and dust can protect against radiation. A dusty crust can hide reflective surfaces. If the outer layer vents gas when warmed, that venting could mask small changes in motion, because outgassing is a normal comet behavior. This does not prove anything, but it explains why the camouflage idea sounds plausible to some listeners. The disguise would not need to be perfect. It would only need to be good enough to look ordinary from far away. The scientific response to this line of thinking is not to dismiss it with ridicule and not to accept it on excitement. The response is to define what would count as strong evidence. A persistent radio signal with a non-natural pattern would matter. A repeated infrared heat source inconsistent with sunlight heating and natural cooling would matter. A reflective glint that behaves like a flat surface turning with controlled orientation would matter. A sequence of trajectory changes that cannot be explained by outgassing models, rotation states, and thermal physics would matter. And a close-range detection by an instrument like Juno, even if it is small, would matter, because it would be harder to blame on telescope noise or distance uncertainty. This is why Juno's silence would be reassuring, but not the end of the story. If Juno sees nothing unusual, it supports the natural explanation. If it sees something, it provides a new test. Either way, the next steps remain the same. keep measuring, tighten the orbit, model the outgassing, estimate the rotation state, and compare predictions against new data as Atlas continues toward Jupiter's gravitational realm. For now, the key idea is simple. A quiet traveler can cross the stars without loud thrust if it relies on time, small nudges, and gravity. A small push at the right moment can shape a path toward a narrow corridor like Jupiter's keyhole, and an icy body, by its very nature, can hide internal structure and mask small forces behind normal-looking activity. That combination is enough to keep the question open in a cautious way, while the object continues on, drifting through the galaxy and into our neighborhood, carried by gravity and time. Nothing in this situation points to danger. There is no implied threat, no suggestion of harm, and no reason for alarm. What is unfolding here is not a warning story. It is a story about possibility, the kind that widens perspective without creating fear, even if Atlas turns out to be entirely natural. Even if every unusual detail ultimately traces back to ice, dust, heat, and gravity, its behavior still aligns with ideas that are central to long-distance motion through space. Clean trajectories, very small nudges applied at critical moments, quiet movement over enormous distances, patience measured not in days or years, but in centuries. In space, arriving loudly is inefficient. A large, obvious burst of energy announces itself and wastes effort. Whether an object is natural or engineered, the most efficient paths are usually the quiet ones. Gravity does most of the work. Small adjustments, applied early or at sensitive points, produce large downstream effects. This is not speculation. It is how interplanetary missions are designed, and it is how natural objects migrate over time. A hypothetical long-lived probe would not need engines firing constantly. It would not need to reveal itself. If it had a task observing, mapping, sampling, or simply passing through it, could accomplish that task without drawing attention, especially if it blended into a population of objects that astronomers already expect to see. That idea leads to a simple, almost unavoidable question. If something wanted to move quietly through the sky of a young technological civilization, what would it look like? From far away, the answer is not a shiny object or a bright signal. It would look ordinary. It would look like something the civilization already understands. A comet fits that description well. Comets are common. They are irregular. They are messy. They release gas and dust. Their paths can change slightly as they warm. Astronomers expect that behavior. A comet-shaped object does not trigger alarm. It does not stand out. It passes through data pipelines as familiar noise. That does not mean Atlas is anything other than a comet. It means only that comets, by their nature, are effective camouflage in a busy sky. A thick, icy crust shields interiors from radiation. A dark, carbon-rich surface absorbs light. Outgassing masks small changes in motion behind a process that is already accepted as normal. From a distance, everything appears routine. A dusty body approaches the sun, releases vapor, and moves on. Whether there is anything beneath that surface is a separate question, and one that cannot be answered by imagination alone. It can only be addressed by data. Both possibilities, fully natural and something more complex, sit within the same larger sense of cosmic wonder. They do not cancel each other out. They simply represent different branches of explanation. And before choosing between them, there is another factor that deserves careful attention: timing. Why now? Why this year? Why this particular geometry near Jupiter? Why this moment in our broader history? If Atlas is purely drifting, then its arrival is coincidence layered on coincidence. Space is large, and eventually unlikely things happen. That explanation remains valid. But if Atlas is carrying anything at all, even something passive, then time itself becomes part of the equation. In the universe, timing is not decoration. It is often the main constraint. Most interstellar visitors pass through star systems at unremarkable moments, quiet centuries, long stretches when nothing much is changing. They arrive when gravity delivers them, not when anyone is watching. Atlas did not arrive in a quiet moment. It appeared during a phase of the Sun known as solar maximum. Solar maximum is part of the Sun's natural activity cycle, which rises and falls over roughly 11 years. During this phase, the Sun becomes more magnetically active. Dark sunspots appear more frequently, magnetic fields tangle and snap. Solar flares release bursts of high-energy radiation, including X-rays. Coronal mass ejections throw vast clouds of charged particles into space. None of this means the Sun is unstable. It means it is energetic. For observers, solar maximum creates noise. Radio signals become harder to interpret. Spacecraft experience increased interference. Earth's magnetic field responds to incoming particle storms. Instruments saturate more easily. Data that is normally clean becomes fuzzy. The Sun, in simple terms, gets louder. Atlas entered the inner solar system during this loud phase. Then, on top of that, it passed through solar conjunction, moving behind the Sun from Earth's point of view for about 35 days. Our instruments could not track it properly. The glare overwhelmed sensors. The geometry blocked clear observation. Solar conjunction alone creates a blind spot. Solar conjunction during solar maximum creates a deeper one, a double layer of observational difficulty. From a purely practical standpoint, if anything subtle were to occur, that window would be hard to see through. A small change in motion, a release of material, a shift in orientation, none of those would register clearly in real time. They would only appear later as a discrepancy between prediction and observation. That is exactly what happened. Again, this does not prove intent. It highlights timing. Timing also applies on the human side of the story. Humanity today is very different from humanity even a few decades ago. Our planet is surrounded by satellites. Communication networks fill near-Earth space with radio signals. Navigation systems broadcast continuously. Radar sweeps track debris and objects. Telescopes scan the sky nightly. We are louder, brighter, and more visible than any previous generation. As we move through the late 2020s, this trend accelerates. Programs like Artemis return humans to the moon. New heavy-lift launch systems change how often and how cheaply large objects reach space. Missions prepare to return samples from Mars. Private companies deploy large satellite constellations. New space telescopes come online. Deep space tracking networks improve in sensitivity and coverage. For the first time, humanity is not just living on a planet. It is extending outward in a sustained, organized way. From far away, this matters. A distant observer would not see cities or borders. It would see radio leakage. It would see artificial signals. It would see changing orbital traffic. It would see a planet transitioning from quiet to active. There is a window where a civilization becomes detectable, but not yet fully self-aware in a cosmic sense. Not silent anymore, but not omniscient either. 2025 sits squarely in that window. Not too early, when Earth's skies were dark and radio quiet. Not too late, when observation systems may become so dense and sensitive that subtle anomalies are quickly flagged and understood. Right now, humanity is visible enough to study, but still limited enough to miss quiet details. That makes the timing of Atlas feel unusual, even if it remains coincidental. When you place the pieces together, the pattern becomes clearer. A solar cycle, that increases background noise, a month-long observational blackout, a civilization expanding its presence into space, an interstellar visitor that changes course precisely when we cannot see it, a trajectory that leads not toward Earth, but toward Jupiter, a region of deep gravity and limited monitoring. Each element alone has an ordinary explanation. Together, they form a configuration that invites attention without demanding a conclusion. This is where the idea of alignment becomes useful. Alignment does not require intention. It simply describes overlapping conditions that reinforce each other. In science, many discoveries begin with alignment rather than certainty. Something appears at the right time, in the right place, under the right conditions, to be noticed only partially. The partial nature of the observation becomes part of the story. There is a quote often attributed to Carl Sagan that captures this mindset well. Coincidence is common, patterns are rare. Coincidences happen constantly. Patterns emerge when coincidences line up in structured ways. Whether the atlas timing represents a true pattern or an illusion created by hindsight remains open. What matters is that the structure is coherent enough to examine. You can picture the timeline without adding emotion to it. A sun near the peak of its activity cycle, instruments dealing with increased noise, a predictable but unavoidable observational gap, a small but well-timed change in motion, a path shaped toward Jupiter rather than toward the inner planets. None of this implies urgency. None of it suggests threat. It simply suggests that if something were to pass quietly, this would be an effective way to do it. At the same time, timing does not have to mean purpose. Nature often produces rare alignments without design. Planetary resonances form naturally. Stable asteroid swarms appear without planning. Gravitational keyholes exist because of geometry, not intent. A rare overlap of cycles can create a moment that feels meaningful because it is uncommon, not because it was chosen. This is why the question does not demand an answer right now. The value lies in the asking. Is Atlas a coincidence? Is it a carefully shaped natural trajectory? Is it something quietly intentional? Each possibility carries different implications, but none require panic. The universe does not owe us simple explanations, and it often reveals its most interesting puzzles through subtlety rather than spectacle. As you let the idea rest, what remains is not tension, but calm curiosity. The mystery is not loud. It does not rush. It unfolds slowly through timing, geometry, and careful measurement. Cycles overlap. Blind spots appear. Objects pass through at moments when observation is imperfect. Sometimes those moments feel coordinated, even when nothing is touching. That is the invitation here, to notice how often the universe arranges events so that meaning emerges softly at the edge of coincidence, not as a warning, not as a message, but as an opportunity to look more closely at how things line up, how forces interact, and how timing can shape what we are able to see and understand. If timing matters, then destination matters even more. In space, position defines opportunity. The most influential places are not marked by borders or terrain, but by gravity. Gravity creates invisible slopes and basins, regions where motion becomes easier in some directions and harder in others. In that sense, the solar system has its own topography, shaped entirely by mass. And outside the sun itself, the highest ground in that landscape belongs to Jupiter. Jupiter's mass is enormous. It is so large that space bends steeply around it, forming the deepest gravitational well among the planets. This is not a subtle effect. Jupiter contains more than 300 times the mass of Earth, and that mass reshapes the motion of nearby objects on a grand scale. Asteroids cluster near it, Comets are redirected by it. Fragments from the early solar system still trace patterns set by Jupiter's influence billions of years ago. Where gravity is strongest, motion becomes organized. The region where Jupiter's gravity begins to rival the Sun stretches more than 50 million kilometers across. This hill sphere is not just an abstract boundary, it is a vast domain where trajectories can be captured, bent, or stabilized. Within it, objects can settle into long-lived paths or be redirected with very little additional energy. In practical terms, it functions like a fortress built not of walls, but of force. From a gravitational high point like this, remarkable things become possible. An object approaching Jupiter does not need engines or fuel to change course dramatically. All it needs is the right approach geometry. A single pass through Jupiter's gravitational field can increase speed, decrease speed, or redirect motion toward almost any part of the solar system. One path can send an object inward toward Earth. Another can guide it toward Mars. Another can fling it outward toward the Kuiper belt, or even beyond the Sun's influence entirely. Gravity does the work. Energy is borrowed from the planet's motion and returned later, all without propulsion in the conventional sense. This is why Jupiter has been used repeatedly as a gravity assist target for human spacecraft. Missions like Voyager, Galileo, Cassini, and New Horizons relied on Jupiter's mass to reach destinations that would otherwise be difficult or impossible. This is not an exotic trick. It is standard orbital mechanics. Jupiter offers access. From its domain, the rest of the solar system lies downhill. There is another feature that makes Jupiter's region uniquely valuable: the Trojan asteroids. These are two enormous swarms of objects that share Jupiter's orbit around the Sun, one leading the planet and one trailing it. They sit near stable gravitational points known as Lagrange points, specifically L4 and L5. These locations are dynamically calm. Objects placed there can remain for millions or even billions of years, with very little change to their orbits. The Trojan swarms are not small collections. They contain tens of thousands of known objects, many of them several kilometers across. They form extended clouds rather than neat clusters, creating a complex environment of rocks and ice moving together through space. From a distance, they blend into the background. From nearby, they provide cover. An object among them does not stand out easily, especially when observation is infrequent. From such a position, much of the solar system is visible. The inner planets trace predictable paths. Earth's orbit is easy to monitor. Mars, the asteroid belt, and even incoming interstellar objects can be observed from a stable vantage point. And because Jupiter's gravity dominates the region, small adjustments can be made efficiently. This is not science fiction. It is a straightforward consequence of how gravity shapes motion. All of this brings the focus back to Atlas and the path it is following. The trajectory does not aim toward Earth. It does not target Mars. It does not dive toward Jupiter's moons. Instead, it approaches the edge of Jupiter's hill sphere, the ridgeline of the highest gravitational ground in the planetary system. That choice of destination, whether intentional or accidental, carries weight. Reaching that ridge changes what is possible next. It is like watching an object move toward a position where options multiply. From that point, many futures become accessible with minimal effort. A natural object could arrive there by chance. A guided object might arrive there by design. Both possibilities fit within known physics. Neither requires urgency or fear. What matters is the role the position plays in shaping outcomes. This is not a story about conflict or conquest. It is a story about perspective. In any system governed by gravity, position determines leverage. A single location can provide insight into everything moving around it. Jupiter's domain offers that kind of overview. It is the place where long-term dynamics become visible, where patterns of motion converge. Seen in this light, Atlas's clean trajectory takes on a specific meaning. It is not rushing. It is not diving. It is approaching carefully, aligning with the invisible contours of the gravitational landscape. A natural traveler might end up there through rare coincidence. A guided traveler might aim for it, because the advantages are obvious. Both interpretations remain calm, grounded, and scientifically acceptable. As this idea settles, the tone remains steady. There is nothing here that demands fear. The image is one of clarity rather than threat. The solar system has hills and valleys defined by gravity, and Jupiter stands at the summit among the planets. Any object that reaches that summit gains access to the full architecture of planetary motion. But where data becomes sparse, imagination tends to grow louder. This has always been true. Silence creates space for stories. With Atlas, that silence was not brief. It lasted for more than a month. For roughly 45 days, there were no new measurements, no updated images, no fresh trajectory refinements. This was not due to secrecy or failure. It was the result of geometry and physics. Atlas passed behind the Sun in a configuration known as solar conjunction. During this time, telescopes on Earth are effectively blinded by solar glare. Even the most advanced observatories cannot look through the intense light of the star that sustains life here. This conjunction occurred during a solar maximum, when heightened solar activity adds additional noise. Charged particle storms interfere with radio systems. Radar becomes less reliable. Space-based instruments face increased interference. For that entire period, observation went quiet. That quiet created a vacuum, and into that vacuum flowed speculation. Some of it was mild, some of it was imaginative, some of it was deeply unfounded. Stories began to circulate suggesting exotic metals detected in Atlas's tail, as if advanced materials were dissolving into sunlight. Others claimed that a metallic object had been seen near Jupiter's leading Trojan region. Another suggested that agencies had quietly revised the trajectory without disclosure. The most dramatic rumors claimed that the Juno spacecraft had already seen something unusual and that the data was being withheld. These stories spread easily because they fit the shape of the mystery. Atlas truly does have an unusual trajectory. It truly did experience a small course change during an observational blackout. It truly is heading toward a region of space that is dynamically significant and rarely monitored in detail. When real facts feel unusual, the human mind looks for explanations that match the emotional weight of that feeling. Humans are not comfortable with empty spaces in understanding. When information is missing, narratives rush in to fill the gap. This is not a flaw unique to modern culture. It is a fundamental feature of how minds work. We connect dots, we search for meaning, we turn uncertainty into story. Most conspiracy theories begin with a legitimate question. Why did the trajectory shift? Why did it happen during the blackout? Why Jupiter? Why this timing? These are reasonable questions. They are scientific questions. They are exactly the kind of questions that drive careful analysis and better models. But some conclusions move beyond evidence. Claims that information is being hidden, claims that the object is a weapon, claims that a probe is already operating in secret. These ideas do not come from data. They come from fear, imagination, or the desire for a universe that feels more dramatic than it actually is. And this is where science does its real work. Science does not reject mystery, and it does not treat curiosity as a weakness. Science simply insists on one thing: evidence. That principle is often summarized by the reminder attributed to Carl Sagan that extraordinary claims require extraordinary evidence. At this moment, in the case of Atlas, there is no extraordinary evidence pointing in any single direction. There is no signal, no image, no physical measurement that forces a dramatic conclusion. What exists instead is something quieter and more difficult to interpret. There is absence, there are gaps, there is silence. That silence is not created by secrecy. It is not the result of hidden data or withheld discoveries. It comes from the limits of observation. Telescopes cannot see through the Sunday radio system's struggle during periods of intense solar activity. Spacecraft are rare, slow, and positioned according to trajectories planned years in advance. The universe is vast, and even our most advanced instruments operate within narrow windows of opportunity. Compared to the scale of space, our view is still fragile. When information disappears under those conditions, silence is not suspicious. It is expected. Yet silence has a side effect. It invites interpretation. When data stops flowing, human imagination fills the gap. Some interpretations are careful and restrained. Others stretch beyond what evidence can support. In the case of Atlas, rumors and theories flourished during the observational blackout, not because people were careless, but because uncertainty naturally creates narrative pressure. Even so, when the noise settles, one fact remains steady. Nothing about Atlas suggests danger. Nothing in its behavior points toward hostility or threat. Its motion is slow, smooth, and predictable. It is not accelerating toward Earth. It emits no radiation beyond what is expected from a cold, icy body. It broadcasts no signals. Its path shows no sharp turns or aggressive maneuvers. Whatever Atlas is, it is not acting in a way that implies urgency or risk. With that understanding, the surrounding speculation begins to lose its edge. The more extreme stories fade into the background. The counter-arguments, reminding us to stay grounded in physics and observation, become easier to accept. What remains is curiosity. Not an anxious curiosity, but a calm one. The kind that encourages patience rather than fear. The kind that motivates careful observation instead of rushed conclusions. And when you step back far enough, Atlas no longer feels isolated. It becomes part of a broader context. Interstellar objects are not hypothetical anymore. They are a recognized population. Space between the stars is not empty. It contains debris, fragments, and travelers shaped by forces far beyond our solar system. Atlas is one instance in a sequence that has only recently become visible to us. The first confirmed interstellar visitor appeared in 2017. It was named Oumuamua, a Hawaiian word often translated as scout or messenger. Oumuamua entered the solar system quietly and left just as quietly, moving fast, on a path that did not loop back. It was detected late, already outbound, giving astronomers only a brief window to study it. Even in that short time, it challenged expectations. Oumuamua did not display the familiar signs of a comet. There was no visible tail, no surrounding cloud of gas, no dust plume reflecting sunlight. Yet, its motion revealed a slight acceleration away from the sun that gravity alone could not explain. Normally, such acceleration comes from outgassing, but no gas was detected. This contradiction forced scientists to consider unusual natural explanations, such as hydrogen outgassing that was difficult to observe, or an extremely thin and porous structure. Others proposed more speculative ideas. The debate itself was a sign of how limited the data were. With so little information, multiple models could fit the observations. 2 years later, in 2019, a second interstellar object arrived, named 2I Borisov. It looked almost comforting by comparison. Borisov behaved like a classic comet. It had a bright coma, a well-defined tail, and clear jets of gas and dust. It fit neatly into existing models. For a moment, it seemed to resolve the tension created by Oumuamua. Interstellar objects could be ordinary after all, but closer analysis complicated that picture. Borisov's dust grains were unusually fine. Its internal structure appeared remarkably uniform. Its velocity as it entered the solar system was higher than expected for a random interstellar wanderer. None of these details proved anything extraordinary, but together, they suggested that even normal interstellar comets might not be quite like the ones formed around our Sunday. Borisov was familiar, but also subtly different. Now comes the third visitor, 3I Atlas. And Atlas does not settle the debate. Instead, it blends the previous cases. Like Borisov, it shows cometry features, a coma, a tail, dust, and gas release. Like Oumuamua, it shows a form of non-gravitational behavior that appears clean and directional rather than chaotic. Its trajectory bends toward a region of space with unusual precision. Its course shifts during a period when observation is impossible, and the change, though small, has meaningful consequences. 3 visitors, 3 distinct behaviors. One breaks the rules, one follows them almost too perfectly. One occupies the space in between. Patterns in science rarely arrive fully formed. They emerge slowly, through comparison, repetition, and context. When these 3 objects are considered together, a quiet pattern begins to take shape. Not a conclusion, but a question that grows harder to ignore. This is where ideas like the interstellar gardener hypothesis enter the discussion. The name sounds poetic, but the idea itself is restrained. It does not propose invasion, communication, or interference. It suggests that if advanced civilizations exist, they might explore the galaxy the way scientists explore ecosystems, by sending out many small, long-lived probes, not to announce themselves, but to observe, to catalog, to learn. In this framework, most probes would drift endlessly through interstellar space, never encountering anything of interest. Some would pass through star systems without slowing. A small fraction might interact with planets or gravitational structures. Fewer still might settle into stable regions where long-term observation is possible. The vast majority would go unnoticed. Only a handful would ever be detected, and even then, detection would be brief and incomplete. This idea does not require advanced science beyond what we already understand. It relies on patience, durability, and time. In a galaxy billions of years old, time is abundant. A probe does not need to hurry. It does not need to signal. It does not need to return. It only needs to survive and record. Even a very slow process becomes effective when multiplied across millions of years. Seen through this lens, the diversity of interstellar visitors makes sense. Oumuamua could be a fragment shaped by extreme conditions in another system. Borisov could be a pristine comet formed far from any star like ours. Atlas could be something that combines natural appearance with structured motion. None of these interpretations are confirmed, but together they suggest that interstellar space may contain a wide variety of objects, shaped by processes we are only beginning to recognize. If intelligence exists elsewhere, curiosity would not be a uniquely human trait. Curiosity is a logical outcome of complexity. A system capable of understanding its environment would naturally seek information. That drive does not require emotion, culture, or even consciousness as we define it. It requires only feedback and adaptation. Quiet observation would be the most efficient strategy. When this idea is connected back to Jupiter, the logic becomes even clearer. Jupiter's Hill sphere and Trojan swarms offer stable, long-term positions with minimal energy cost. They are far from Earth's constant scrutiny, yet close enough to monitor the inner solar system. They provide gravitational leverage and observational advantage without requiring intervention. For any object seeking a long-term perch, Jupiter's domain is unmatched. At the same time, this perspective does not diminish the possibility that Atlas is entirely natural. Nature often produces structures and behaviors that appear purposeful when viewed in isolation. Orbital resonances, stable points, and clean trajectories can arise without intent. The universe does not need design to create elegance. Gravity alone can produce order that feels meaningful. What matters is not choosing an answer prematurely, but recognizing the context. Atlas exists within a growing catalog of interstellar objects. Each one adds a data point. Each one refines our expectations. Together, they hint that our solar system is not isolated, but part of a larger exchange of material moving between stars. As we watch Atlas approach Jupiter's gravitational realm, we are also watching ourselves change. Our instruments improve, our coverage expands, our understanding deepens. The next interstellar visitor will be detected earlier, studied longer, measured more precisely. Patterns that are now subtle may become clearer, and beyond these visitors, we continue to discover distant worlds, planets orbiting other stars, moons with oceans, atmospheres rich in chemistry, systems that challenge what we thought was typical. In 2025, one such discovery reminded us that the universe still has the ability to surprise us, not through spectacle, but through quiet alignment of evidence. Atlas is part of that reminder. Not a threat, not a message, but a prompt, a signal that the universe is larger, older, and more interconnected than we once believed, and that we are only beginning to notice the travelers passing through it. Somewhere far beyond our sun, astronomers reported a result that felt quietly important. A moon, orbiting a distant giant planet, showed signs of an atmosphere, not a thick blanket of gas like a giant planet, and not something you could see directly, but a thin layer that left a trace in light. The observation started in a familiar way. A distant star dimmed for a short time as an object passed in front of it. That drop in brightness is called a transit. What made this case different was what showed up inside the starlight during the transit. As the star's light passed through whatever surrounded the moon, certain wavelengths were absorbed more than others. Instruments measured those missing parts of the light and turned them into a spectrum, a kind of chemical fingerprint. This method is called transit spectroscopy. The core idea is simple. Light goes through air. Molecules in that air block specific colors. If you measure which colors are missing, you can infer what kinds of molecules are present. This does not mean the moon is alive. It does not mean oceans or biology or anything dramatic. An atmosphere is not a guarantee of life, but it is a guarantee of chemistry. It means the moon is not just a cold rock with nothing happening. It has a boundary layer where particles move, react, and change over time. That alone matters, because chemistry is the first step toward complexity in any environment we know. Once you accept that moons around other stars can hold atmospheres, it becomes harder to think of moons as minor side objects. They become worlds. They can have surfaces, subsurfaces, skies, and cycles, even if those cycles are slow and cold. That shift in perspective also points back toward our own Jupiter. because Jupiter is surrounded by a large family of moons, at least 79 known ones, each with its own conditions. Some are small and quiet, some are extreme, some are scientifically central to questions about habitability. Europa is one of the most discussed because evidence strongly supports a global ocean beneath its ice shell. The surface is cracked and reshaped, suggesting movement below. Ganymede is remarkable because it has its own magnetic field, the only known moon with that property. Io is a world of intense volcanism, driven by tidal forces, where lava reshapes the surface constantly. Callisto is heavily cratered and ancient, preserving a record of early solar system history. These moons are not just scenery, they are environments. They are storage places for ice, rock, salts, and complex chemistry. They are natural laboratories where energy and matter interact in ways that can persist for long periods. This matters for the Atlas story because Jupiter's region is not just a planet with a strong gravitational pull. It is a system full of places where objects can pass through, linger, and remain stable. If an interstellar object approached Jupiter and ended up captured temporarily or guided into a long-lived orbit, the moons would be among the most meaningful nearby environments. A moon can provide shelter from some external forces, depending on location and radiation conditions. It can also provide a quiet backdrop where faint signals or small changes might be easier to separate from the noise of the sun and the inner planets. Even if we are only talking about natural processes, moons are where long-term chemistry can store information about the past. They keep records in ice layers, surface composition, and trapped particles. So a reported detection of an atmosphere around a distant exomoon becomes more than an isolated result. It becomes a reminder that moons are common outcomes of planet formation, and that many of them may be active in ways we are only starting to detect. What we learn about distant moons helps us interpret the moons close to home. And if moons elsewhere can hold thin atmospheres, then moons in our own system remain some of the most important places to watch, especially around a giant like Jupiter. There is another idea that connects quietly to this, and it is about storage and endurance. An atmosphere can hold chemical signatures that reflect what is happening on a world's surface or below it. In that sense, an atmosphere can act like a slow record. It can carry evidence of processes that are otherwise hidden. That naturally raises a broader point. Memory, in the physical sense, does not belong only to biology. Information can be stored in many ways, in chemical ratios, in trapped gases, in crystal structures, in magnetic fields, and in engineered systems, if those systems exist. If you step away from astronomy for a moment and look at what has been developing in physics and computing, one of the long-standing challenges has been how to preserve delicate information over time in a hostile environment. In quantum computing, the basic unit is a qubit, short for quantum bit. A qubit can store information in a way that depends on quantum states, which are powerful but fragile. The main problem has always been stability. Noise from heat, vibration, electromagnetic interference, and radiation can cause a qubit to lose its state. When that happens, the information is effectively gone. That is why early quantum systems needed constant correction and careful isolation. They could not hold still for long. In recent years, researchers have reported progress on extending how long quantum information can remain coherent, meaning how long it can hold its state without collapsing into noise. This often involves better materials, improved shielding, colder operating temperatures, and error correction methods that can detect and repair mistakes without destroying the quantum information. One of the barriers discussed in this field is the error floor, the point where reducing errors becomes difficult because leftover sources of noise stop improving with standard fixes. Pushing that floor downward is a major goal. because it increases how long information can survive and how reliably it can be retrieved. Progress here does not mean quantum memory is now easy or that it can run unattended for centuries. It does mean something important. The problem of long-lived information storage in quantum systems is not frozen in place. Each improvement expands the window of what is physically achievable. It makes a concept that once seemed purely theoretical feel more like an engineering challenge with a path forward. This matters when people think about interstellar travel, not because it proves anything about Atlas, but because interstellar travel is mainly a problem of survival over time. Distances between stars are so large that a slow craft could take centuries or longer to cross them. A system traveling that long has to endure radiation, micrometeoroid impacts, thermal cycling, and simple material aging. Conventional electronics can degrade over long durations. Sensors can fail. Memory can corrupt. Power sources can weaken. Even if a craft uses a quiet propulsion approach, like a sail or a passive gravity path, it still needs something that can persist. A long-lived memory system, whether quantum-based or not, would be central to that endurance. It would allow a system to store navigation data, maintain a mission plan, and preserve information gathered along the way. It would also allow long periods of inactivity. A craft does not need to stay awake the whole time. In fact, for longevity, it would likely spend most of its journey in a low-power state, waking only when conditions matter, such as when entering a star system, passing near a major planet, or encountering radiation levels that require changes in shielding or orientation. If, and only if, Atlas were carrying an engineered system of any kind, it would need something like that, not because the idea is exciting, but because it is practical. A system meant to survive very long travel must store information reliably while spending long periods doing almost nothing. It must be able to wake, act briefly, and then return to a stable resting state. It must maintain identity over time, meaning it must not lose its internal records of what it is and what it is doing. That concept can sound intimidating, but the basic logic is straightforward. Long travel needs long memory. Long memory needs protection from noise. Noise comes from the environment, and the environment in interstellar space is harsh, but also cold and quiet in certain ways. A well-designed system could use deep cold to help preserve sensitive components. It could use shielding to reduce radiation exposure. It could use redundancy, storing the same information in multiple ways. And it could use periods of inactivity to reduce wear. This still does not point back as evidence. It points back as a reminder that what once felt impossible can become possible over time. Human technology is already exploring ways to store and protect information at scales that were not realistic a few decades ago. If we are beginning to understand longer-lived quantum states and stronger error control, then a civilization older than ours, even by a few thousand years, could in principle push these ideas much further if it existed and chose to. That is one reason the Atlas discussion keeps returning to patience and subtlety. A system built for long timescales would not rush. It would not broadcast loudly. It would not rely on constant thrust. It would use gravity, timing, and small adjustments. It would move in ways that look calm because calm is efficient. A traveler that expects to operate over centuries would not be shaped by short-term urgency. Its decisions, if it made any, would be slow and planned. The same approach applies to navigation. Memory alone is not enough for a long journey. Any traveler, natural or engineered, needs a way to move through a landscape. And in space, the landscape is not made of roads or landmarks. It is made of invisible structure, the gravitational fields of stars and planets, the pressure from starlight, the flow of charged particles, and the subtle forces that add up over time. This is where the story naturally turns toward the next requirement. Even the most patient traveler needs more than the ability to remember. It needs a map, a way to navigate not just through stars and planets, but through the deeper, invisible scaffolding that shapes how the universe moves. And that brings us to the next piece of the puzzle. If you could see gravity directly, you would not see empty space. You would see structure, not walls or roads, but a landscape made of pull, gentle slopes where motion is easy, steep basins where paths bend and tighten, long ridges where small changes matter. We often talk about space as if it is nothing, but space has shape because mass shapes it. Stars, planets, and every cloud of matter leave a mark. And beyond what we can see with light, there is more mass than we can directly observe. That hidden mass is what scientists call dark matter, and it adds its own contours to the galaxy's gravitational terrain. In 2025, researchers pushed closer to something that has been a goal for a long time, measuring that hidden structure in a more direct way. The tool behind it sounds technical at first, but the idea is approachable. It comes from what are called pulsar timing arrays, a network built from natural clocks spread across the Milky Way. A pulsar is a neutron star, the dense core left behind after a massive star collapses. Many pulsars rotate with extreme regularity. As they spin, they send out beams of radio waves. If the beam sweeps past Earth, we detect a pulse after pulse. The timing can be so steady that it rivals the best clocks we build on Earth. That steadiness is the key. When something changes the space between us and the pulsar, even slightly, it can shift when those pulses arrive. The shift can be tiny, on the order of a billionth of a second, but it can still be measurable when you collect data over long periods and compare many pulsars at once. That is what a pulsar timing array does. It does not rely on one pulsar. It compares many. Astronomers monitor dozens of these cosmic clocks and look for timing patterns that line up across the sky. If one pulsar arrives early or late on its own, that could be local noise or a measurement issue. But if many pulsars show related timing shifts in ways that match a shared distortion in space-time, then you have a real signal that something large is shaping the geometry. This technique is best known for its role in the search for low-frequency gravitational waves, the slow ripples in space-time expected from supermassive black hole pairs. But the same basic approach also helps scientists probe large-scale gravitational structure. Any broad, persistent curvature in space-time affects travel time for light and radio waves. If you can measure those timing changes well enough, you can begin to infer the shape of the gravitational field that caused them. In simple terms, you are learning the slope of the terrain by watching how long it takes a signal to cross it. The result, in 2025, was not a perfect, finished atlas of dark matter. Science rarely delivers that in one step. What researchers reported were stronger constraints and early three-dimensional reconstructions of gravitational gradients, the direction and steepness of the downhill pull in different regions. It was not a map of stars. It was not a map of glowing gas clouds. It was a map built from timing, showing where gravity seems to rise and fall in ways that visible matter alone cannot explain. A sketch of the galaxy's unseen scaffolding. This is where the idea becomes useful, not just interesting. A chart of constellations helps you point a telescope. A chart of dark matter gradients, if you could refine it enough, helps you navigate. Interstellar travel is not a matter of drawing a straight line from one star to another and simply going. Space is filled with competing pulls. Stars tug, Planets bend paths. Dust clouds add drag at tiny levels. Radiation pressure from starlight can nudge objects over time. Even the galaxy's overall gravitational field curves motion on very long scales. If you tried to travel between stars while ignoring all of that, you would constantly drift off course. You would spend energy correcting your path again and again. It would be like trying to steer a boat across an ocean while refusing to account for currents. You might still get there, but you would waste effort fighting what you could have used. But if you knew the shape of the gravitational landscape well enough, you could do something smarter. You could ride the terrain. You could choose routes that followed gentle gradients instead of crossing steep basins. You could avoid regions where gravity would trap you into long detours. You could use natural slopes to reduce the number of course corrections. That does not mean you get motion for free. It means you use the universe's structure as part of the plan. The same way sailors once used winds and tides instead of treating the sea as a flat surface. You can picture it simply. Imagine you are moving across a surface of hills and valleys. Walking straight across the steepest slopes costs more effort. Following a shallow ridge costs less. Gravity is not a solid surface, but the logic is similar. If you can read the gradients, you can choose the path that requires the smallest push to stay on track. Over distances measured in light years, even small savings become large. A tiny reduction in corrections, repeated many times, becomes a major difference in what kind of vehicle you need and what kind of endurance it must have. This connects back to Atlas in a way that stays calm and careful. If Atlas is purely natural, then its smoothness remains unusual. And the question is, why? If Atlas were engineered long ago, drifting quietly through interstellar space, then a navigation strategy based on gravitational contours would make sense. It would not need loud engines. It would not need frequent maneuvers. It would only need to stay aligned with the landscape, letting the terrain do much of the shaping. It would move the way a floating object moves in a slow current, not because it chooses each ripple, but because it follows the structure already present. That thought does not need drama to be interesting. It is logical. We are just beginning to measure these gradients in a serious way. If humanity, early in its technological era, is starting to read the galaxy's hidden structure through pulsar timing, then a civilization even 1,000 years older, or 10,000 years older, or far older, could in principle build navigation models that are more precise than anything we can currently manage. We tend to navigate by light, because light is what our senses and tools evolved to use. But light can be blocked by dust. It can scatter. It can be absorbed. It can mislead when the medium is messy. Gravity does not get blocked. Gravity does not dim behind a cloud. You cannot hide mass from gravity. You can hide it from light, but not from its pull. So it is reasonable to imagine that a more advanced navigator would trust gravity more than brightness. We watch the sky and measure light curves. A more ancient traveler might treat gravity like the true map. As that idea settles, it produces a quiet kind of awe, not an excited rush, but a steady sense that the universe may be less random than it appears, not because it is scripted, but because it follows rules. There is a hidden geometry we are only beginning to read. If a traveler like Atlas exists in any form beyond a natural comet, that traveler would not need magic. It would need the same things any long mission needs: longevity, navigation, and leverage. In this story, longevity points toward durable memory. Navigation points toward gravitational structure, including dark matter gradients. Leverage points toward Jupiter, the highest gravitational ground among the planets. With those pieces in place, the Atlas question shifts in tone. It becomes less like a warning and more like a whisper of possibility. The universe is vast and ancient, but it is also structured. Patterns exist, roots exist, stable perches exist, and we are small inside it, but not fragile in the way fear suggests. We are capable of learning. That is the point. Now the focus returns to the simple scene outside your window. Far out in the dark, Atlas is still only a faint point. It does not blaze across the sky. It does not announce itself. It moves without urgency. Any tale it carries is thin and cold, fading into the background of space. It is just a traveler continuing along a path shaped by forces we can model, even if we do not yet understand every detail of why this particular path looks so clean. And here, in a quiet room on Earth, you are doing what humans do best when faced with a hard question. You are watching. You are listening. You are letting evidence and uncertainty sit side by side without forcing a quick answer. You can trace the chain of events that brought Atlas into focus. There was a small shift in its path that became visible only after it emerged from behind the Sunday. There was a trajectory that tightened toward Jupiter's invisible threshold. There is Juno, not hunting, but present, the only active spacecraft close enough to serve as a nearby witness. There is the possibility, gentle and not asserted as fact, that Atlas could be more than it seems. There is the timing of its arrival during a noisy phase of solar activity. There is the idea of gravitational high ground near Jupiter, where a path can be redirected with minimal effort. There are the other interstellar visitors that came before it, each strange in a different way. There are moons, near and far, that show signs of atmospheres and chemistry. There are technologies we are only starting to build that speak to endurance and long memory. There are methods we are only starting to use that speak to reading the galaxy's hidden gravitational structure. Piece by piece, a larger picture forms. Not certain, not proven, not a claim, just a coherent set of connections that make the question worth holding. Atlas does not show signs of danger. It does not change what tomorrow looks like. It is not aimed at Earth. It is not rushing inward. It is simply gliding on, following a line that stands out mainly because it is precise. And that is where the word terrifying fits in a careful, scientific sense. Not because something is attacking us, but because the universe can be this exact. A natural object should not often land on a corridor with odds like 1 in 26,000. A drift hidden in solar glare should not so neatly align with a gravitational keyhole. Silence should not carry so many open possibilities. And yet, in rare cases, it does. The unknown does not demand anything from you. It does not require you to solve it tonight. It offers a question, and the question can be held without fear. The sky will still behave the way it always does. The moon will rise on schedule. Earth will keep rotating. Your surroundings will remain the same. You are safe. You can let your breathing slow and your shoulders relax. Curiosity does not need closure to be worthwhile. It can exist on its own. We look up, not because we expect immediate answers, but because the act of understanding matters. Whatever Atlas is, it will still be there tomorrow, and the day after that, moving steadily along a path shaped by gravity and time. It does not rush you. The universe rarely does. It invites you to wonder at your own pace, without forcing a conclusion. Atlas continues on its path, unaffected by the questions we place upon it. It does not accelerate, it does not transmit signals, and it does not turn toward Earth. It simply advances along a trajectory shaped by gravity and time, notable only for how narrowly defined that path is. The motion is steady, quiet, and consistent with known physical forces. yet precise enough to draw careful attention. Nothing in this behavior demands an immediate conclusion. Nothing suggests urgency. The available data does not indicate danger, and it does not confirm deliberate design. What it presents instead is an unusual alignment of factors, a trajectory that passes through a narrow gravitational corridor, a period of invisibility during solar conjunction, a destination near the strongest gravitational high ground in the planetary system, and a set of physical explanations that are each ordinary on their own, but less so when considered together. In science, this is often how deeper questions emerge, not from dramatic signals, but from patterns that remain intact under repeated examination. Atlas will continue to be observed. Its orbit will be refined, and its interaction with Jupiter's gravitational domain will be measured with increasing precision. Over time, those measurements will clarify whether the simplest explanations are sufficient or whether revisions are required. For now, Atlas is exactly what the evidence allows it to be: an interstellar visitor moving through the solar system along a path governed by familiar physics, yet marked by an unexpected level of exactness. That precision is not unsettling because it threatens us, but because it highlights how structured the universe can be, and how much of that structure we are only beginning to recognize.